What if everything you think you know about time is wrong? Picture a reality where the past, present, and future aren't separate moments marching in a straight line, but a tangled web where cause and effect blur into something far stranger. For centuries, we've treated time as a constant, an unshakable river flowing in one direction. But what if that's just an illusion? Today, we're diving into 28 revolutionary theories that could shatter our understanding of time's very origin. These ideas don't just tweak the edges of physics, they tear up the rulebook entirely, suggesting that time might be emergent, cyclical, or even a side effect of deeper cosmic forces we're only beginning to grasp. Think about the last time you felt a déjà vu, that eerie sense that you've lived a moment before. Now imagine that sensation isn't a glitch in your brain, but a faint echo of a universe where time folds back on itself. Some of the theories we'll explore propose exactly that: loops where the future influences the past, or parallel timelines brushing against each other like threads in a vast tapestry. Others suggest time isn't fundamental at all, but something that emerges from the chaos of quantum particles, like temperature arising from the motion of atoms. It's not just science fiction, these are real, testable ideas being debated by the brightest minds in cosmology and quantum physics. So why does any of this matter? Because if we can crack the mystery of time, we might unlock secrets about the birth of the universe, the nature of black holes, and even the ultimate fate of reality itself. This isn't just about abstract equations, it's about rewriting the story of existence. Over the next minutes, we'll journey through concepts so profound they bend the mind, from holographic universes to cosmic inflation, from wormholes to the possibility that time itself could be a kind of memory. Each theory is a piece of the puzzle, and together they paint a picture of reality far stranger and more beautiful than we ever imagined. Buckle up, this is going to change how you see everything. The Big Bang wasn't just the birth of space and matter. It might have been the moment time itself flickered into existence. Imagine standing at the edge of creation, where the universe was compressed into an infinitely dense, scorching point. In that singularity, the very fabric of reality warped so severely that our ordinary rules of cause and effect simply didn't apply. This theory challenges something we take for granted: that time has always been there, ticking away in the background. But what if time, like the universe, had a definite starting point? Some physicists argue that asking what came before the Big Bang might be as meaningless as asking what's north of the North Pole. Without the framework of time, there's no before to speak of, just an incomprehensible state where the concept of duration dissolves. Yet not all scientists agree. Alternative models suggest time could have existed in some primordial form, a chaotic quantum foam where tiny fluctuations eventually sparked the expansion we call the Big Bang. Think of it like bubbles forming in a boiling pot. Our universe might be just one bubble among countless others, each with its own timeline. If that's true, time didn't begin with the Big Bang. It merely reshuffled into the orderly flow we experience today. This raises even wilder questions. Could other universes have entirely different arrows of time, where effects precede causes or entropy runs backward? The implications ripple outward. If time had a beginning, will it also have an end? Some theories suggest the universe's expansion could eventually reverse, collapsing back into a singularity, a big crunch where time itself might unravel. Others propose a colder fate, where the cosmos spreads into infinite silence, and time becomes irrelevant in a universe too sparse for change. Either way, this theory forces us to confront the unsettling idea that time might not be eternal, but a temporary feature of our cosmic neighborhood. Whether it emerged from quantum randomness or was born in the fire of the Big Bang, one thing's certain: our understanding of time is far from complete, and the truth might be stranger than we've ever dared to imagine. What if our universe isn't the only one, but just a single bubble floating in an endless cosmic sea? Eternal inflation theory paints a picture of reality so vast it defies imagination, a multiverse where new universes constantly bud off from an ever-expanding quantum foam, each with its own unique physics, its own rules, even its own version of time. In this dizzying landscape, time might not be a universal constant but a local phenomenon, behaving differently in each pocket universe. Some could experience time flowing backward, others might have timelines that loop like tangled strings, and in some, time might not exist at all. This idea challenges the very foundation of how we perceive reality. Think of it like a forest where every tree grows at its own pace, some straight and tall, others gnarled and twisted. Our universe just happens to be one where time flows in a way that allows stars to burn, planets to form, and life to emerge. But why? One compelling answer comes from the anthropic principle. We observe time behaving this way because it's the only way we could observe it. In universes where time is chaotic or reversed, complex structures like galaxies, let alone conscious beings, might never arise. We're here because our timeline permits it. The implications grow even stranger when you consider how these bubble universes might interact. Could gravitational waves or quantum fluctuations from neighboring universes leave faint imprints in ours, like echoes from another dimension? Some theories suggest that if two bubble universes collided, their timelines might briefly merge, creating anomalies in the cosmic microwave background, clues that physicists are actively searching for. And if time operates differently elsewhere, what does that mean for the nature of causality itself? In a multiverse, the idea of a single, linear history might be an illusion, replaced by an infinite tapestry of possible pasts and futures. Perhaps most mind-bending of all is the question of whether time is even fundamental or just an emergent property, like wetness emerging from individual water molecules. In some pocket universes, the very concept of sequencing events could be meaningless, replaced by a state of pure potential where everything happens at once. It's a humbling thought. The steady tick of our clocks might not be a universal truth, but a quirk of our cosmic address, one thread in a grander weave we're only beginning to glimpse. Einstein's theory of relativity didn't just reshape space, it shattered time. Picture the universe not as a series of moments ticking by, but as a vast, unchanging block where past, present, and future exist all at once. In this block universe, time isn't a river flowing from one event to the next. It's more like a frozen landscape, with every moment laid out permanently, like frames in a film reel. Your birth, your first steps, the moment you're hearing these words, they're all equally real, just occupying different coordinates in space-time. This idea turns our everyday experience on its head. We feel time passing, but according to relativity, that's just an illusion of perspective, like mistaking a single page in a book for the entire story. But if the block universe is real, what does that mean for free will? If the future is already out there, fixed in the cosmic structure, are our choices just illusions? Philosophers and physicists have wrestled with this for decades. Some argue that our sense of decision-making is like a character in a novel believing they're steering the plot, when in reality, every twist was written long ago. Yet quantum mechanics throws a wrench into this deterministic view. Experiments show particles don't have definite states until observed, suggesting reality might be more like a story being written as we go, not a pre-recorded tape. The tension between these ideas, relativity's frozen block and quantum mechanics' fluid uncertainty, has sparked radical new theories. Perhaps time isn't fundamental at all, but something that emerges from deeper processes, like how temperature emerges from the motion of atoms. Some researchers propose that our perception of time's flow comes from the way quantum probabilities collapse into definite outcomes, creating the illusion of a moving now. Others suggest time might be a side effect of entanglement, the spooky connection between particles that Einstein famously dismissed. Here's where it gets even stranger. If time is emergent, could it change or even break down under extreme conditions? Near a black hole's event horizon or in the earliest moments of the universe, the familiar arrow of time might fray, leaving physics without a clear past or future. This could explain why time seems to flow in one direction despite most physical laws working equally well backward or forward. Entropy, the universe's tendency toward disorder, might not be the full story. So is time real or just a trick of consciousness? The block universe says it's all there, while quantum experiments hint at something more dynamic. Maybe the truth lies somewhere in between, a universe where time is both a dimension and an emergent property, shaped by the act of observation itself. One thing's certain, the more we learn, the less time behaves like the steady, familiar rhythm we thought it was. And that raises a haunting question: if time is an illusion, what else might we be missing? Quantum entanglement is one of the most baffling phenomena in physics. Two particles become so deeply linked that changing one instantly affects the other, no matter how far apart they are. This happens faster than light could travel between them, seemingly smashing our usual notions of cause and effect. If time is supposed to enforce a strict order where causes come before their effects, then entanglement laughs in the face of that rule. It's as if the universe secretly has a backchannel where particles communicate without waiting for time's permission. This raises a radical possibility. What if time isn't a fundamental feature of reality, but something that emerges from the way quantum systems interact? Think of it like watching a movie. From the outside, you see the whole story at once, every scene fixed in place. But when you press play, time seems to flow as one frame follows another. Some physicists suggest our experience of time might work the same way, emerging from the way entangled particles settle into definite states, creating the illusion of sequence. Experiments support this mind-bending idea. When scientists measure entangled particles, their properties snap into alignment instantaneously, as if the distance and the time it would take for information to cross that distance doesn't matter. It's not that information is traveling faster than light. It's that the particles exist in a timeless state where before and after lose their meaning. This has led to theories like the quantum gravity model, where space and time arise from a network of entangled connections, like pixels forming an image. The implications ripple outward. If entanglement underpins time, then black holes where gravity warps spacetime to extremes might be places where time unravels entirely. Near a singularity, particles could become so entangled that cause and effect break down, leaving physics without a clear timeline. Even stranger, some models suggest the entire universe could be a web of entanglement, with time emerging from the way quantum links propagate and decohere. So is time just a collective hallucination? Not exactly, but it might be more like a dance than a river, a rhythm created by countless quantum interactions rather than an absolute backdrop. If that's true, then the steady tick of clocks isn't marking some universal flow, but reflecting something far more mysterious: the hidden conversations between particles, stitching reality together one entangled moment at a time. What if the flow of time isn't built into the fabric of the universe, but more like a movie projected onto the walls of reality? The holographic principle turns our understanding of dimensions upside down, proposing that everything we experience, including time, might just be a shadow cast from a deeper, simpler reality. Imagine standing in front of a waterfall, watching the ripples and swirls. The water seems alive with motion, but what if those patterns aren't fundamental? What if they're just reflections of something happening beneath the surface? That's the essence of this theory, time as a side effect, not the main event. This idea didn't come from nowhere. It emerged from the study of black holes, where physicists faced a paradox. When matter falls into a black hole, it seems to vanish, but quantum mechanics insists information can't be destroyed. The solution: that information isn't lost. It's smeared across the black hole's event horizon like data etched onto a cosmic hard drive. If a collapsing star can encode its entire history onto a two-dimensional surface, could the universe itself be doing the same thing? Some theorists argue yes, suggesting that our three-dimensional world, complete with the illusion of time, is just a projection from a vast, flat boundary we can't perceive. Think of it like a hologram on a credit card, a flat surface that creates the illusion of depth when you tilt it. In this model, time isn't a river flowing forward. It's more like frames in a film, each moment already encoded on the universe's hidden screen. This would mean your sense of moving through time is as much an illusion as the 3D image on that credit card. Even stranger, if time emerges from this deeper layer, it might not be smooth or continuous at all. Just as a digital video is made of discrete pixels, time could be stuttering forward in quantum jumps too tiny for us to notice. The implications are staggering. If time isn't fundamental, then the arrow of time, why we remember the past but not the future, might not be written into the laws of physics. Instead, it could arise from the way information gets scrambled as it's projected into our 3D world. This could explain why entropy always increases, why cause always precedes effect, without needing time to be a primary ingredient of reality. It's like realizing the plot of a novel isn't driven by the pages themselves, but by the author's choices outside the book. Could we ever test such a wild idea? Surprisingly, yes. Scientists are looking for faint imprints in the cosmic microwave background, the afterglow of the Big Bang, that might reveal a pixelated structure to spacetime. Others are studying quantum gravity models where spacetime pixels become visible at extreme energies. If the universe really is a hologram, then at some fundamental level, time might not exist at all, just a vast, timeless code giving rise to the changing world we perceive. So next time you check your watch, consider this. The ticking seconds might not be measuring something real, but reading out a cosmic mirage, a shadow play cast from the edges of existence. If the holographic principle is right, then time isn't the stage on which the universe unfolds its part of the performance. An elaborate illusion convincing us the show is moving forward when, beneath the surface, every moment might already be written in the stars. Einstein's spacetime flows like a river, smooth and unbroken, but what if that's not how the universe really works? Loop quantum gravity paints a radically different picture. Time as a series of tiny, indivisible moments, like frames in a cosmic film reel. Imagine zooming in on reality until you see its pixels not just for space, but for time itself. In this view, the universe doesn't change continuously. It updates in discrete quantum jumps, each a fundamental tick of existence. This isn't just a tweak to physics, it's a complete overhaul, one that could solve some of cosmology's deepest mysteries. Take the Big Bang singularity, where equations break down and infinity rears its head. Loop quantum gravity replaces that mathematical nightmare with something far more elegant, a quantum bounce. Picture the universe not as a fiery explosion from nothing, but as a rebound from a previous collapse. Time doesn't begin its cycles like a cosmic heartbeat. This could mean our universe wasn't born in isolation, but emerged from the death of another in an endless dance of expansion and contraction. The singularity vanishes, replaced by a quantum threshold where gravity becomes repulsive, pushing space-time apart again. But if time comes in chunks, how small are they? Theoretical calculations suggest these quantum moments could be staggeringly brief, around 10 to the power of -43 seconds, a timescale so short it makes a nanosecond feel like an eternity. At this level, the smooth flow of time we perceive would be an illusion, like watching a movie and missing the individual frames. This raises a provocative question. Could the universe be processing reality like a computer, calculating each frame before rendering the next? Some physicists speculate that if spacetime has a pixelated structure, there might even be a fundamental limit to how fast information can change, a cosmic frame rate governing all of existence. The implications ripple outward. If time is granular, then black holes might not be infinitely dense points, but quantum objects where spacetime's structure reaches its smallest possible scale. Even the arrow of time, why we remember the past but not the future, could emerge from the way these quantum steps interact, like dominoes falling in one direction but not the other. And if the universe really operates in discrete steps, it might leave fingerprints in high-energy phenomena like gamma-ray bursts, where tiny fluctuations could reveal spacetime's underlying graininess. Yet for all its promise, loop quantum gravity isn't without challenges. Unlike string theory, which suggests extra dimensions and vibrating strings, this framework keeps space and time front and center, but reimagines them as a dynamic web of interconnected loops. Visualizing this isn't easy. Think of spacetime not as a blank stage, but as a constantly evolving network of relationships, where each loop's quantum state defines the geometry of reality itself. It's a universe built not from stuff but from processes, a cosmic symphony where time itself is the rhythm. So is time truly digital? The answer could redefine not just physics but our place in the cosmos. If reality updates in quantum steps, then free will might not be an illusion just constrained by the universe's refresh rate. And if the Big Bang was a bounce, then time might be infinite, with no beginning or end, just endless transformation. One thing's certain, in a granular universe, the clockwork precision we take for granted is far stranger and more beautiful than we ever imagined. Time crystals sound like something ripped from a sci-fi novel, structures that don't just exist in space, but pulse rhythmically in time itself. Unlike ordinary crystals, where atoms arrange in repeating spatial patterns like a diamond's lattice, time crystals tick through cycles without any energy input, defying the usual rules of thermodynamics. Picture a clock that winds itself forever, or a pendulum that swings without ever slowing down. This isn't perpetual motion, it's a newly discovered phase of matter where the very structure of reality dances to a timeless beat. The discovery sent shockwaves through physics because time crystals shouldn't exist. The second law of thermodynamics states that disorder always increases, energy dissipates, systems wind down. Yet time crystals sidestep this decay by settling into a stable, repeating rhythm, like a cosmic metronome immune to entropy's grip. How? They exploit quantum entanglement, with particles locking into a synchronized dance where their collective state cycles predictably, even in the absence of external pushes. It's as if the universe has a hidden tempo, and these crystals are tuned to its frequency. Could this bizarre behavior hold clues about time's deepest mysteries? Some theorists speculate that time crystals might reveal a hidden symmetry between time and space, a clue that time, like dimensions, could have a crystalline structure at quantum scales. Imagine space-time not as a smooth fabric, but as a layered lattice where time itself vibrates. If true, this could reshape our understanding of causality, suggesting that the arrow of time isn't an absolute rule, but an emergent property of how quantum systems interact. Even wilder is the possibility that time crystals exist naturally in the cosmos. Neutron stars, with their crushing densities and bizarre quantum effects, might harbor these structures in their cores, their relentless spin echoing the rhythmic pulses of a time crystal. Or perhaps the early universe, in its seething chaos, birthed primordial time crystals that left faint imprints in the fabric of reality. If we could detect such relics, they'd be fossils of time's fundamental architecture, proof that the universe ticks in ways we've barely begun to fathom. The implications stretch beyond theory. Time crystals could revolutionize quantum computing, offering stable, error-resistant qubits that harness their rhythmic coherence. They might even challenge our notions of equilibrium, showing that certain systems never truly settle. They just find new ways to move. This isn't just a curiosity, it's a crack in the foundation of physics, hinting that time might be more malleable, more structured than we ever dreamed. So next time you glance at a clock, consider this. The steady march of seconds might not be the only way time flows. Deep in the quantum realm or the heart of distant stars, reality could be pulsing to a rhythm all its own. A rhythm that turns our linear experience of time into just one note in an infinite symphony. What if the universe at its core doesn't even have a clock? The Wheeler-Dewitt equation, a thorny piece of math from the frontiers of quantum gravity, proposes exactly that, a reality where time isn't just flexible or emergent, but entirely absent from the fundamental equations. Imagine stripping away every second, every tick of the cosmic metronome until you're left with pure, frozen physics. No past pushing into the future, no arrow pointing anywhere, just a static snapshot of everything that is, was, or will be. At first glance, this seems impossible. After all, we feel time passing. Seasons change, stars burn out, memories accumulate. But this equation whispers a radical idea. What if change itself is an illusion, a trick played by quantum entanglement? To grasp how this could work, think of a movie projected onto a blank wall. The film isn't moving, it's just a sequence of still frames. But when played fast enough, our brains stitch them into motion. The Wheeler-Dewitt equation suggests reality might operate similarly. At the quantum level, particles don't evolve through time. They correlate with each other in a vast, timeless web. Your sense of now isn't a point on a timeline, it's more like a spotlight sweeping across these correlations, creating the illusion of sequence. This isn't just philosophy. Experiments with entangled particles already show that quantum systems can behave as if cause and effect aren't strictly linear, with measurements here instantly influencing states light years away. But if time isn't fundamental, why does it feel so real? Here's where things get fascinating. Just as temperature emerges from the jostling of atoms, even though no single atom is hot, time might emerge from the way quantum systems interact. Picture a crowd doing the wave in a stadium. No single person moves forward, but the collective motion creates the illusion of a traveling pulse. Similarly, the universe's flow could be a statistical effect, with trillions of quantum events conspiring to create what we perceive as duration. This would explain why time seems to arrow forward. Entanglement spreads in one dominant direction, like ink dispersing in water, giving rise to the irreversible march of entropy we experience. Critics argue this view leaves no room for dynamic processes like consciousness or free will. If the universe is a frozen block, how do we make choices? Proponents counter that the block isn't lifeless, it's more like a symphony where every note exists simultaneously, and our perception plays them in order. Your decisions are still real, just part of a richer, timeless geometry. Some versions of the theory even suggest that without a fundamental time variable, the Big Bang wasn't an event in time, but a boundary where time emerges. Like realizing the edge of a map isn't a place on the terrain, but the limit of the paper itself. So where does this leave us? Staring into a cosmic hall of mirrors, where the most familiar aspect of existence, time, might be the universe's most elaborate sleight of hand. If the Wheeler-Dewitt equation is right, then clocks don't measure time. They measure our participation in a quantum illusion, a dance of correlations so precise we mistake it for a river. The equations on a physicist's chalkboard could be describing a reality where when is no more fundamental than up or down, just a perspective, not a law. And that forces a humbling question. If time is an emergent mirage, what other certainties might dissolve under scrutiny? Black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate puzzle boxes, locking away secrets that could redefine time itself. When matter crosses a black hole's event horizon, it doesn't just vanish from sight. According to Stephen Hawking's groundbreaking work, it might take the very fabric of causality down with it. This is the black hole information paradox. Quantum mechanics insists that information, the detailed state of every particle, can never be destroyed, yet black holes seem to erase it permanently. Imagine burning a book and being told the ashes still contain every word, just scrambled beyond recognition. That's the dilemma physicists face, and the stakes couldn't be higher. If information can vanish, the laws governing time's arrow why we remember the past but not the future might unravel at the singularity. So how could information escape a black hole's grip? One radical idea is the firewall hypothesis, which suggests the event horizon isn't the smooth gateway Einstein predicted, but a searing wall of high-energy particles. Anything crossing it wouldn't glide gently into oblivion. It'd be vaporized instantly, its information smeared across the horizon like data encoded on a cosmic DVD. This solves the paradox, but at a bizarre cost. Two observers could experience wildly different realities. Someone falling in would hit the firewall and burn up, while an outsider watching from afar would see them slow down and freeze at the horizon, thanks to time dilation. It's as if the universe can't decide which outcome is real, leaving time itself fractured at the edge. Another solution leans into the holographic principle, where the 3D universe is a projection from a 2D surface. In this view, a black hole doesn't destroy information. It compresses it onto its event horizon like a celestial hard drive. Every particle swallowed leaves a faint imprint, a quantum pixel in a vast cosmic mosaic. Over eons, as the black hole evaporates via Hawking radiation, that information could leak back out, scrambled but intact. Think of it like boiling water. Steam carries away hidden details of the liquid's original state, even if we can't easily decode them. If this is true, then time near a black hole might not end. It just gets rewritten in a language we don't yet understand. But the wildest implication: black holes could be laboratories for time's extremes. Near the singularity, gravity warps space-time so severely that cause and effect might swap places. You couldn't just see the future, you'd be forced to interact with it, like a character in a movie suddenly aware they are rewinding. Some models even suggest that black holes birth new universes, with their singularities acting as cosmic reset buttons where time reboots under new rules. It's a haunting thought. Our universe's orderly timeline might owe its existence to some long-ago black hole's chaotic demise. The paradox forces us to confront a deeper question: is time's flow universal, or just a local quirk of our cosmic neighborhood? If black holes can bend, scramble, or even erase it, then the steady tick of clocks might be more fragile than we ever imagined. Every solution to the paradox firewalls, holograms, baby universes paints time not as a backdrop, but as a dynamic player in the drama of physics, one that can stretch, shatter, or even reboot under the right conditions. And that leaves us with a humbling realization. To understand time's true nature, we might need to stare into the abyss and let it stare back. Time's relentless forward march feels so natural that we rarely question it. But physics has no law demanding that time must flow in one direction. The equations work just as well backward. So why do eggs splatter but never unsplatter? Why do we remember yesterday but not tomorrow? The answer might lie in entropy, the universe's tendency toward disorder. The second law of thermodynamics states that entropy always increases, creating an invisible arrow that gives time its direction. But this raises a deeper mystery. If entropy always grows, why was it so astonishingly low at the Big Bang? The universe began in a state of near-perfect order, a fragile arrangement so unlikely that physicists compare it to finding a deck of cards pre-sorted by suit and number. One provocative explanation is that our universe isn't alone, it's half of a mirrored pair, with a twin where time flows backward. In this two-headed arrow model, the Big Bang wasn't a beginning but a pivot point between two universes, each with entropy increasing away from that moment. From our perspective, time moves forward as chaos spreads. From the other universe's view, we're the ones living in reverse. Picture two detectives standing back to back at a crime scene, each convinced they're facing the right way. Both perspectives could be equally valid. While this idea sounds like pure speculation, it emerges naturally from certain interpretations of quantum gravity, where the equations describing the early universe are eerily symmetric. But there's another twist. Entropy's rise might not be about particles jumbling randomly, but about quantum possibilities collapsing into definite outcomes. Every time a quantum system chooses a state, an electron spinning up or down, a photon taking one path instead of another, it leaves behind a trail of discarded alternatives like footprints in the sand. This process, called decoherence, could be the true engine of time's arrow. The more quantum systems interact, the more their entangled histories branch out, creating an irreversible flow of information, a kind of cosmic forgetfulness that makes the past fixed and the future open. Could we ever reverse this process? Hypothetically, if you could undo every quantum interaction in a cup of coffee, unscrambling the milk swirls until it's separated perfectly, you'd effectively rewind time in that tiny system. But scaling this up to the universe is another matter. The computational power needed would dwarf all the energy in existence, and even then, quantum randomness might foil the attempt. Still, the mere possibility hints at something profound. Time's arrow isn't carved in stone. It's a statistical tendency, a cosmic habit rather than an absolute rule. This leads to the most unsettling question of all. If entropy defines time's flow, what happens when the universe reaches maximum entropy? In the far future, when stars have burned out and black holes evaporated, the cosmos might settle into a lukewarm soup of particles, evenly dispersed and unchanging. Without energy gradients to drive change, would time lose all meaning? Some theories suggest yes, that in this heat-death, the universe would enter a timeless state, a frozen tableau where before and after cease to exist. Yet others propose more exotic fates, like quantum fluctuations birthing new big bangs from the void, restarting time's cycle anew. The arrow of time isn't just a curiosity, it's the thread stitching together cause and effect, memory and identity. Without it, reality would be a hall of mirrors with no way to distinguish history from prophecy. And that's the real wonder. The universe didn't have to be this way. The fact that time flows at all might be the deepest clue we have about the nature of existence. a whisper from the Big Bang that order, however fleeting, is written into the fabric of reality. What if every attempt to change the past was doomed from the start, not by some cosmic rulebook, but by time itself bending to preserve its own consistency? The Novikov self-consistency principle turns the classic time travel paradox on its head. Imagine stepping into a time machine to prevent a historical disaster, only to realize your actions were the disaster all along. Your meddling didn't rewrite history, it was history, a closed loop where cause and effect snake back on themselves like an Ouroboros eating its own tail. This isn't just a thought experiment, it's a serious proposal from Russian physicist Igor Novikov, suggesting the universe might have a built-in mechanism to prevent contradictions, like a cosmic editor trimming away impossible plot twists. Take the infamous grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, how could you exist to do the deed? Novikov's answer is eerily simple: you couldn't. The universe would conspire to stop you, whether through a jammed gun, a sudden slip on the stairs, or some other unlucky intervention. Your free will would feel real, but every choice would funnel you toward the one outcome that keeps the timeline consistent. It's like living in a novel where the author has already written the last page, and no amount of improvisation can change the ending. This idea gains traction in quantum mechanics, where particles seem to know their future states. Experiments like the delayed choice quantum eraser show measurements made now can retroactively influence events that already happened. On a cosmic scale, this could mean time loops aren't just possible, they're inevitable. Picture a universe where every paradox resolves itself quietly, like ripples canceling out in a pond. Those eerie moments of déjà vu, they might not be glitches in your brain, but fleeting glimpses of a timeline folding back on itself, a momentary alignment of events that had to happen. But here's the twist: Novikov's principle doesn't necessarily mean the future is set in stone. Some interpretations suggest multiple self-consistent timelines could coexist, each a variation where time travelers play different but equally inevitable roles. Think of it like a choose-your-own-adventure book where every path leads to the same final chapter, just by different routes. This could explain why the universe appears fine-tuned for life, because only in timelines where every quantum dice roll just happened to allow stars, planets, and observers do those observers exist to ponder the coincidence. The implications stretch beyond time machines. If self-consistency governs reality, then free will might be an illusion woven from layers of quantum inevitability. Your choices could be the universe's way of reconciling its own math, like a pianist improvising within a scale they didn't invent. Even stranger, this might hint at a deeper structure to spacetime, one where loops and knots aren't anomalies, but the hidden scaffolding holding existence together. So next time you feel déjà vu's whisper, consider this. You might not be remembering the past, but brushing against a future that's already written and always was. The quantum realm is a place where certainty dissolves into probability, where particles exist in blurred superpositions until observation forces them to choose a state. But what if those choices aren't random at all? The many worlds interpretation offers a breathtaking alternative. Every quantum decision creates a new universe, splitting reality into parallel branches where all possible outcomes play out. Time in this view isn't a single thread but a sprawling tree, its limbs stretching endlessly into alternate futures and pasts. Your life isn't one path, it's countless paths, each real, each unfolding simultaneously in ways you'll never see. Think of it like a choose-your-own-adventure book where every page turn spawns new editions of the story. When you flip a coin, one universe sees heads, another tails, but neither outcome cancels the other. Both exist just in separate branches of the cosmic tree. This solves one of quantum mechanics' biggest puzzles: why particles seem to know how to behave when measured. They don't. Every possible result happens. We just experience one slice of the multiverse. The implications for time are staggering. If every quantum event branches reality, then some universes might have clocks running backward, or moments repeating like a broken record. In one branch, you might arrive early to a meeting, in another, stuck in traffic forever. This isn't science fiction, it's a direct consequence of the math. When particles entangle, their correlations stretch across these branching timelines, weaving a tapestry where every what if becomes a what is. But how could we ever prove such a wild idea? Surprisingly, there are clues. Quantum computers leverage superposition to explore multiple solutions at once, like testing every maze path simultaneously. If the many worlds interpretation is correct, these machines aren't just calculating, they're briefly merging with their alternate selves, borrowing answers from parallel realities. Even stranger, some physicists speculate that faint echoes from nearby branches might explain quantum interference patterns, like whispers from universes almost but not quite like our own. The most mind-bending twist: you're already living this fractal existence. Right now, versions of you are making different choices, surviving disasters you narrowly avoided, or thriving in careers you never pursued. Time's flow isn't fixed, it's a kaleidoscope fracturing with every breath. So the next time you hesitate at a crossroads, remember, somewhere you didn't. And both versions are equally real. What if everything you perceive, the screen in front of you, the memories you hold, even the passage of time isn't real, but a fleeting hallucination of a lone, disembodied mind? This is the chilling premise of the Boltzmann brain paradox, a thought experiment that pushes the limits of entropy and infinity to their breaking point. Named after physicist Ludwig Boltzmann, it asks a haunting question. In an eternal universe where disorder reigns, couldn't random fluctuations occasionally create self-aware observers, fully formed with false memories of an unlived past? Statistically, given enough time, even the most improbable events must occur, including a brain, complete with consciousness, blinking into existence from pure chaos. The paradox emerges from a simple but unsettling truth. If the cosmos lasts forever, entropy, the tendency toward disorder, will eventually dominate, leaving the universe a cold, featureless void. But quantum mechanics allows for rare reversals, moments when particles spontaneously arrange into order. Given infinite time, these fluctuations could produce anything: a single hydrogen atom, a chair, or an entire galaxy. And yes, even a fully functioning brain, convinced it's living in a rich, coherent world. The implications are dizzying. If Boltzmann brains are possible, they're inevitable, and statistically, there should be far more of them than real, evolved observers like us. So how can you be certain you're not one? Critics argue this scenario is absurd, a reductio ad absurdum of infinite time theories. After all, a Boltzmann brain's experiences would be incoherent. One moment you're sipping coffee, the next you're a floating mind in the void. But proponents counter that your present sense of continuity could be part of the illusion, a brief flicker of coherence before dissolution. Think of it like a dream where the narrative feels solid until you wake up and realize none of it held together. Worse still, some versions of the paradox suggest time itself might be a construct of these fleeting minds, with no objective flow, just an endless sea of momentary observers, each believing they're part of a timeline. So where does this leave our understanding of time? If Boltzmann brains are possible, then the arrow of time, our unshakable sense that the past is fixed and the future open, might be a local quirk, a transient bubble of order in an otherwise timeless chaos. It's as if the universe is a dark ocean, and we're not even waves but single drops convinced we're riding a tide. Some physicists sidestep the paradox by arguing that certain cosmological models, like eternal inflation, prevent infinite entropy states. Others embrace it as a clue that time's flow is an emergent property, not a fundamental feature. A story consciousness tells itself to make sense of randomness. The ultimate nightmare that there's no way to disprove you're a Boltzmann brain. Every memory, every scientific discovery, even this sentence could be a figment of a mind that didn't exist a moment ago and won't exist in the next. But here's the twist. If the universe can conjure a consciousness complex enough to ponder its own existence, doesn't that suggest reality is far stranger and more malleable than we ever imagined? Whether a warning about infinity's perils or a call to rethink time's nature, the paradox forces us to confront an unnerving truth. The fabric of reality might be woven from questions, not answers. What if the ticking of every clock, the aging of every star, and the unfolding of every life is just an illusion, lines of code executing in some unfathomable supercomputer? The simulation hypothesis takes our deepest questions about time and flips them into a cosmic mystery. Could reality be a construct, with time itself reduced to nothing more than a variable in an alien programmer's equation? This isn't just philosophy. Some scientists argue that if the universe operates like a digital simulation, time might not flow smoothly but update in tiny, discrete steps, like frames in a video game too fast for us to perceive the gaps. Think about the way video games render worlds. When you walk through a virtual forest, the trees don't exist until you look at them. The system generates them on demand to save processing power. Now imagine the same principle applied to reality. Quantum mechanics already shows particles don't have definite properties until measured, as if the universe is optimizing its computations. Those strange quantum jumps, they might not be fundamental physics, but processing delays, tiny lags in the cosmic GPU as it calculates the next state of reality. Even the speed of light could be a built-in limit, like a system's clock speed, preventing calculations from happening too fast and crashing the simulation. But if time is programmed, who or what controls it? A creator could pause, rewind, or accelerate time at will, like a player fiddling with a game's settings. Ancient myths speak of gods stretching days or freezing battles. Could these be garbled memories of simulation glitches? Modern physics has its own anomalies. Particles communicating instantly across distances, quantum states that seem to know future measurements, even mathematical constants so finely tuned that altering them by a hair would make stars and life impossible. These aren't just quirks, they're potential fingerprints of a coded universe where time is a tool, not a law. The most unsettling implication: if time is algorithmic, free will might be an elaborate illusion. Your choices could feel real, but they'd be predetermined by the simulation's initial conditions, like a character in a game believing they're making decisions when every action was scripted long ago. Yet some theorists push back, suggesting that true consciousness, if complex enough, could introduce genuine unpredictability, forcing the simulation to adapt in real time. After all, even the most advanced program can't precompute every possible thought a billion minds might have. So how could we ever test this? One approach looks for pixelation in space-time, evidence that reality has a finite resolution at the smallest scales. Another searches for repeating patterns in cosmic constants, like a programmer reusing chunks of code. And if we ever discovered an actual glitch, a contradiction in physics, a mathematical inconsistency, it might be the closest thing to a blue screen of death for the universe. Until then, the simulation hypothesis remains a mirror, reflecting our deepest fears and fascinations back at us. That time might not be a river, but a loop of ones and zeros, and we're all just characters in a story someone or something is still writing. What if the Big Bang wasn't a beginning, but a cosmic reset, one chapter in an endless cycle of creation and destruction? The Ekpirotic universe theory throws out the idea of a one-time explosive birth, replacing it with something far grander: time as an infinite loop where universes collide, rebound, and are reborn over and over. Picture two sheets of paper floating parallel in a dark room, except these aren't ordinary sheets. They're brains, hypothetical higher dimensional surfaces drifting through a hidden realm of space. When they smash together, the impact unleashes enough energy to forge an entirely new cosmos, complete with its own arrow of time, its own laws, its own story. Our universe might just be the latest iteration in an eternal sequence, a phoenix rising from the ashes of its predecessor. This isn't just poetic speculation. The theory elegantly solves one of cosmology's biggest puzzles: why the universe seems so finely tuned for life. If time is cyclic, then each collision tweaks the cosmic constant slightly, like a gambler rolling dice until they finally hit the perfect combination. After countless cycles, a universe emerges where particles bond into atoms, stars ignite, and life arises not because of design, but through sheer persistence. It's the ultimate trial and error machine, with time itself as the engine. But how could a collision of invisible brains create everything we see? The math suggests these impacts wouldn't be chaotic crashes, but smooth, almost orchestrated events. As the brains draw near, their gravitational pull stretches space, flattening it into the uniform expanse we observe in the cosmic microwave background. Then, at the moment of collision, energy floods into the newborn universe, mimicking the heat of a Big Bang, but with a critical difference. Unlike the classic singularity, where physics breaks down, the Ekpirotic model avoids infinity altogether. There's no nothingness before, just an endless rhythm of contraction and rebirth. The implications ripple through time's arrow. If the cycle continues, our universe will eventually contract, galaxies drawing nearer until the next collision resets the clock. But here's the twist: each cycle isn't an exact replay. Tiny quantum fluctuations mean every iteration is unique, like variations on a cosmic theme. You'll never get the same universe twice. Some might harbor life, others could be barren voids. And if the cycles stretch infinitely into past and future, then time isn't a line. It's a spiral, winding through variations of reality with no true start or end. Could we ever find evidence of a previous cycle? Some physicists hunt for faint imprints in the cosmic microwave background, anomalies that might carry scars from a pre-Big Bang existence. Others study gravitational waves, searching for echoes of ancient collisions vibrating through spacetime. If detected, these whispers from beyond time would rewrite our place in the cosmos, revealing that we're not the first universe, and certainly not the last. The Ekpirotic model offers a humbling yet exhilarating vision. That time isn't fleeting but eternal. Not a single spark in the dark, but a fire that burns forever, its embers scattering new worlds with every cycle. And if that's true, then every moment we experience, every sunrise, every heartbeat, is part of a pattern older than existence itself, a rhythm that will outlast even the stars. Quantum mechanics and general relativity are the twin pillars of modern physics, yet when it comes to time, they speak completely different languages. In quantum theory, time is a rigid stage where particles dance to probabilistic rules, an unchanging backdrop against which superpositions collapse and waves interfere. But in Einstein's relativity, time is fluid, stretching and compressing like taffy near massive objects, woven inseparably with space into a dynamic fabric. This isn't just a technical disagreement, it's a cosmic identity crisis. If these two frameworks can't agree on what time is, how can we ever unify them into a single theory of everything? The heart of the conflict lies in their opposing philosophies. Quantum mechanics treats time as an external parameter, something outside the system that ticks uniformly while particles evolve. Picture a stopwatch beside a lab experiment, marking intervals without being affected by the reactions inside. But relativity insists time is part of the system, bent by gravity and motion, its pace varying depending on where you are and how fast you're moving. Near a black hole, clocks slow to a crawl. In empty space, they race. This creates a paradox when we try to merge the theories. Should time be a fixed ruler or a stretchable thread? Some physicists propose a radical solution: time isn't fundamental at all, but an emergent property, like wetness emerging from water molecules. In loop quantum gravity, for example, space-time itself is woven from tiny, discrete loops. Time might arise from their interactions, a collective rhythm rather than a background beat. Another approach, called the Wheeler-Dewitt equation, famously erases time entirely from its math, suggesting our perception of flow could be an illusion born from quantum entanglement. Imagine a cosmic game of dominoes. Each falling piece represents a quantum event, and time is just the sequence we perceive as one knocks into the next. But the most promising bridge between these worlds might be entanglement itself. When particles become entangled, their fates intertwine instantaneously, seemingly bypassing time's constraints. Some theories suggest spacetime itself could be built from these quantum connections, like a vast network where time is just the direction in which correlations propagate. Think of it like a friendship bracelet. The thread's quantum links don't move, but the pattern time's flow emerges from how they're tied. This could explain why time seems to arrow forward. Entanglement spreads in one dominant direction, like ink diffusing in water. The stakes couldn't be higher. If we crack this puzzle, we might finally understand the birth of the universe, where quantum and relativistic effects collided. Was time created in the Big Bang, or did it crystallize from some timeless quantum foam? Even black holes, where relativity predicts time's end at singularities, but quantum mechanics demands information preservation, could hold clues. The answer won't just reshape physics. It'll redefine what it means to exist in a universe where time, our most familiar companion, might be the ultimate cosmic sleight of hand. What if time doesn't flow on its own, but only because we're here to witness it? This radical idea, that consciousness might be the engine driving time's arrow, turns our understanding of reality inside out. Quantum mechanics already shows us that particles exist in blurry superpositions until measured, as if the act of observation forces the universe to make up its mind. Now imagine scaling that up, not just particles collapsing into place, but entire moments crystallizing from possibility into history because a mind is there to perceive them. It's as if time isn't a river carrying us forward, but a path we carve simply by walking. The roots of this theory stretch back to the double-slit experiment, where particles behave differently when watched, suggesting observation shapes reality at the quantum level. Some physicists, like John Wheeler, took this further with his participatory universe hypothesis, where consciousness isn't just a bystander but an active player in creation. Picture a cosmic game of 20 questions where the answers don't exist until someone asks. In this view, the past isn't fixed. It's a story being written retroactively by every measurement, every observation. Your memories might feel like records of solid events, but they could be more like ink drying in real time, shaped by the present moment's need for consistency. But how could something as intangible as consciousness influence time itself? One clue lies in entropy, the universe's tendency toward disorder. While physics says entropy gives time its direction, conscious beings seem uniquely skilled at creating local pockets of order, like assembling atoms into poems or skyscrapers. This reversal of entropy's tide, even temporarily, hints at a deep link between mind and time's flow. Think of a snowflake forming in a storm. Its intricate symmetry emerges against the chaos, just as conscious observation might coax structure from quantum fog. The implications spiral into philosophy. If time requires observers, does it mean the universe before life was timeless, a frozen superposition waiting for the first mind to animate it? Some interpretations of quantum cosmology suggest exactly that, with the Big Bang's initial conditions selected by the eventual emergence of consciousness. It's a modern twist on the old question: if a tree falls in an empty forest, does it make a sound? Now we're asking, without a witness, does time even pass? Critics argue this veers into solipsism, making reality dependent on human perception. But proponents counter that consciousness needn't be human. Any information-gathering system, from AI to alien life, could play the same role. What matters isn't who observes, but that observation happens at all. This shifts time from an absolute backdrop to a relational phenomenon, like how a rainbow only appears when light, droplets, and a viewer align. The most unsettling possibility: if consciousness shapes time, then altering perception could warp time's flow. Near-death experiencers often report time dilating a minute, stretching into hours. Psychedelics can dissolve the sense of sequential events, creating a timeless, eternal now. Even mundane focus, like an athlete in the zone, distorts time's passage. These aren't just quirks of the brain, they might be glimpses of time's true plasticity, revealing how tightly it's woven into the fabric of awareness. So where does this leave us? Either time is an illusion conjured by minds, or consciousness is the universe's way of giving time meaning. Both answers are equally profound and equally humbling. The next time you glance at a clock, consider this: the seconds ticking by might not be measuring the world's rhythm, but yours. If black holes are cosmic vacuum cleaners, relentlessly swallowing everything in their path, then white holes are their rebellious twins, cosmic fire hoses blasting matter and energy outward with unstoppable force. While black holes trap even light behind an event horizon, white holes defy gravity's pull, violently expelling anything that dares to approach. The math of general relativity allows for such objects, but spotting one is another matter. They'd be dazzling beacons in the void, shining with the energy of entire galaxies, yet none have been confirmed. But here's the tantalizing twist: if they exist, white holes could rewrite time's story entirely, turning the universe's history into a mirror reflecting more than we ever imagined. One audacious theory suggests the Big Bang itself was a white hole's eruption, a singular moment when all the energy and matter in our universe burst forth from some unseen cosmic womb. Picture a drain plugged by a black hole in another reality, funneling matter through a hidden channel until it explodes into our cosmos as a white hole. This wouldn't just make our universe the offspring of another, it would imply time might have a symmetrical counterpart. If a black hole's singularity represents time's end, a white hole's explosion could mark its rebirth, like a phoenix rising from its own ashes. The implications are dizzying. Our cosmic timeline might not be a straight line, but a loop, with white holes stitching together cycles of collapse and renewal. But the strangest possibility: white holes could be bridges to alternate realities. In Einstein-Rosen bridges, better known as wormholes, a black hole's crushing gravity might connect to a white hole's eruptive exit, creating a tunnel through space-time. While traversable wormholes remain speculative, the math hints that a white hole's fury could be the other end of a black hole's silence, like two doors swinging open between universes. Imagine tossing a clock into a black hole here and watching it tumble out of a white hole in another timeline, its hands spinning backward. This wouldn't just challenge our linear view of history, it would shatter it, suggesting every moment might branch into infinite echoes across the multiverse. Critics argue white holes violate thermodynamics, spewing order into the cosmos without an obvious energy source. Yet proponents counter that they could be black holes from a reversed timeline, a universe where entropy flows backward, making the end of a black hole in that reality the beginning of a white hole in ours. It's like watching a film reel in reverse. What's collapsed to one observer is creation to another. Recent studies of gamma-ray bursts, brief, violent eruptions in deep space, have found anomalies that don't fit standard supernova models. Could these be white holes flickering to life, their brilliance fading as they exhaust their cosmic fuel? The most poetic idea: if white holes are real, then death and birth might be two sides of the same cosmic coin. Every black hole's end could seed a new universe's beginning, with time not as a line but a mosaic of interlocking cycles. Our universe's expansion, the arrow of time, even the eerie fine-tuning of physical constants, all might trace back to a white hole's primordial scream. So the next time you gaze at the night sky, consider this: somewhere beyond the edge of perception, a mirror reality might be unfolding, its history flowing backward toward a moment when our futures collide. Dark energy isn't just expanding the universe, it might be quietly setting the stage for its ultimate destruction. Right now, this mysterious force acts as a cosmic accelerator, pushing galaxies apart faster and faster. But what if its grip keeps tightening? The phantom energy model paints a chilling picture of the far future, where dark energy doesn't just nudge space apart, it shreds it. Imagine spacetime as a rubber sheet stretched too thin until one day it snaps. Not just galaxies, not just stars, but atoms themselves would be torn asunder, their particles ripped apart by the universe's own expansion. And if spacetime disintegrates, what happens to time? The math behind this Big Rip scenario is as elegant as it is terrifying. Phantom energy, a particularly aggressive form of dark energy, would grow stronger as space expands, creating a runaway feedback loop. First, galaxies would vanish over the horizon, their light stretched beyond detection. Then, gravity's hold would falter, sending solar systems adrift. Stars would be peeled apart, their nuclear furnaces snuffed out as the space between their atoms stretches infinitely. Finally, in the last fraction of a second, even the fabric of matter would unravel, quarks torn from protons, space-time itself fracturing into meaningless chaos. Time, no longer tethered to events or change, would become an empty concept, like a ruler with nothing left to measure. But here's the twist: this apocalyptic finale hinges on dark energy's exact properties. Current observations show it behaving like a cosmological constant, steady and unchanging. Yet if it's even slightly dynamic, if its strength increases with time, the Big Rip becomes inevitable. Some theorists argue this could explain why the universe seems curiously fine-tuned for life. We exist in the brief window before expansion erases all complexity. Others propose exotic physics that might slam the brakes: quantum gravity effects, higher dimensional barriers, or even a hidden symmetry that flips dark energy's script. The most haunting implication: if the Big Rip occurs, it wouldn't just end the universe, it would erase its history. With no atoms left to encode information, no structures to mark time's passage, every trace of existence would dissolve into infinite emptiness. No fossils, no light, no memory of galaxies or civilizations. Time wouldn't just stop, it would lose all meaning, like a clock melting in a furnace. Yet even this bleak scenario sparks radical ideas. Could a post-Rip universe reboot somehow, birthing new spacetime from the wreckage? Or does the rip reveal time's true nature, not as a fundamental feature, but a fragile emergent property, vanishing when the conditions that birthed it collapse? For now, the phantom energy model remains a specter on the edge of cosmology, a possibility both terrifying and exhilarating. It forces us to confront time's limits, not as an abstract concept, but as a thread woven into the fabric of reality, one that might one day fray beyond repair. Whether the universe ends with a rip, a crunch, or a whisper, one truth remains: time's story is still being written, and the final chapter could rewrite everything we think we know. What if time isn't woven into the universe's blueprint, but something far stranger, an illusion conjured by the ceaseless chatter of quantum bits? Emergent space-time theory flips the script on reality, proposing that the stage itself, the very fabric of space and time, isn't fundamental, but a grand mirage rising from deeper, more primitive layers of quantum information. Picture a bustling city at night. From a distance, the glow appears smooth and continuous, but up close, it's made of countless individual lights flickering independently. Space-time might work the same way: a shimmering hologram projected from a hidden network of quantum connections, with time itself as the emergent rhythm of their interactions. This idea didn't spring from pure speculation. It grew from the thorny math of black holes, where physicists discovered that all the information inside a black hole could be perfectly encoded on its two-dimensional event horizon like a cosmic zip file. If a three-dimensional volume's essence can be stored on a flat surface, maybe our entire universe operates the same way. String theory takes this further, suggesting that space-time isn't a fixed arena but a dynamic construct, braided from vibrating strings or woven from quantum entanglement. Time, in this view, isn't a river flowing on its own. It's more like the beat of a drum emerging from the collective vibration of unseen strings. The implications rewrite the rules of causality. If time is emergent, then the now you're experiencing isn't a universal truth. It's a local phenomenon, as relative as the warmth of a cup of coffee. A particle near a black hole and one drifting in deep space might not even agree on the sequence of events, because their time arises from different quantum contexts. This could explain why time seems to flow in one direction. Entanglement spreads like ink in water, creating an arrow of correlation that our brains interpret as the passage of moments. But here's the real mind bender. If space-time emerges, it might not exist everywhere equally. In the quantum realm or at the universe's edges, where entanglement frays, time could stutter, loop, or even vanish entirely. Imagine a computer struggling to render a game's graphics where processing lags, pixels glitch. If space-time is a projection, then black holes might be cosmic dead zones where the quantum processor stutters, leaving time undefined. Even the Big Bang could be reinterpreted not as the birth of time, but the moment quantum information first crystallized into something resembling a timeline. Could we ever test such an abstract idea? Surprisingly, yes. Physicists are hunting for spacetime's pixels in high-energy particle collisions, where tiny fluctuations might reveal the underlying quantum code. Others study quantum computers, where simulating entanglement networks could mimic how spacetime emerges. And if the theory holds, it would mean time isn't just flexible, it's negotiable, a side effect of deeper physics waiting to be decoded. So the next time you check your watch, consider this. Those ticking seconds might not measure an absolute flow, but the hum of a hidden quantum engine, stitching reality together one entangled connection at a time. In a universe where space-time is derivative, time isn't the director, it's just another actor playing its part in a show whose script we're only beginning to read. Einstein's universe runs like clockwork, predictable, smooth, and precise. But down in the quantum realm, time dances to a far wilder rhythm. The time-energy uncertainty principle shatters our classical intuition, revealing that time itself might be fundamentally fuzzy at the smallest scales. Just as you can't simultaneously know a particle's exact position and momentum, there's a cosmic trade-off between measuring energy perfectly and pinning down time with infinite precision. The more tightly you try to grasp one, the more the other slips through your fingers like sand. This isn't a limitation of our tools, it's baked into the fabric of reality, suggesting time might not be the steady, unbroken stream we perceive, but a seething quantum foam where moments flicker in and out of focus. Picture a stopwatch submerged in a bubbling quantum soup. Instead of ticking evenly, its hands would stutter, jumping forward and backward in tiny, unpredictable leaps. These fluctuations are unimaginably brief, lasting around 10 to the power of -43 seconds, the so-called Planck time, but their implications are colossal. If time isn't perfectly smooth, then the very idea of now becomes a statistical illusion, an average over countless quantum leaps too rapid for any clock to capture. It's like trying to measure the ripples in a stormy sea with a yardstick. The closer you look, the more chaotic the motion becomes. This quantum jitter might already be leaving fingerprints in the lab. Particle accelerators occasionally detect anomalies, tiny energy fluctuations that defy standard predictions. Could these be echoes of time's granularity, moments when the universe's hidden uncertainty bubbles up into the observable world? Some theorists speculate that high-energy cosmic rays, which sometimes arrive with slightly more or less energy than expected, are skimming the edge of time's quantum nature, their paths nudged by invisible ripples in the temporal fabric. The uncertainty principle also reshapes how we think about energy itself. In empty space, where we'd expect perfect stillness, quantum mechanics allows for fleeting bursts of energy to materialize out of nothing, so-called virtual particles that pop in and out of existence. These aren't just mathematical quirks. They're responsible for real phenomena like the Casimir effect, where two metal plates in a vacuum inexplicably attract each other. If energy can fluctuate this wildly, and energy and time are quantum partners, then time must be fluctuating too. The vacuum isn't empty, it's a churning ocean of temporal static, where moments dissolve into probability. What does this mean for the arrow of time? If the microscopic flow isn't smooth but a series of quantum hops, then entropy's rise, the steady march toward disorder, might emerge from countless tiny uncertainties adding up. Imagine a pile of sand grains. Individually, each grain's position is unpredictable, but collectively, they always trend toward spreading out. Time's arrow could be a similar statistical effect, a cosmic illusion born from quantum chaos. The most radical implication: if time and energy are fundamentally intertwined, then manipulating one might let us tweak the other. Hypothetical warp drives, which bend spacetime to achieve faster-than-light travel, rely on concentrating enormous energy densities, precisely the realm where time-energy uncertainty reigns. Could future engineers harness these quantum ripples to stretch or compress time intentionally? It's a long shot, but the universe has already shown us that time is far stranger than it seems. For now, the uncertainty principle stands as a humbling reminder. Even time itself has quantum secrets, and the clockwork universe might be more like a jazz improvisation, unpredictable, alive, and infinitely surprising. General relativity holds a secret so bizarre it seems ripped from a time travel thriller, paths through spacetime that curve back on themselves like a snake swallowing its tail. These closed timelike curves aren't just mathematical oddities, they're theoretical highways to the past where cause and effect twist into knots. Picture stepping into a time machine, traveling back to prevent your parents from meeting. only to realize your interference ensured they'd cross paths your existence both the reason for and the result of your own actions. This isn't science fiction, it's the grandfather paradox laid bare, a cosmic riddle where time's flexibility threatens to unravel logic itself, yet the universe might have built-in safeguards. The Novikov self-consistency principle argues that any attempt to alter history would inevitably fail, not through some cosmic police force, but through the sheer improbability of contradictions. Like a river carving its canyon, time would adjust to any interference, bending events subtly to preserve its own coherence. Miss your shot at stopping your grandfather's wedding. Maybe your gun jams or a sudden rainstorm delays your arrival. The universe becomes a master storyteller, editing out plot holes before they can form. But what if consistency isn't the only option? Quantum mechanics offers a wilder alternative. Every paradox spawns a new reality. In this multiverse model, killing your grandfather doesn't erase you, it branches the timeline, creating a parallel universe where you're never born, while the original history rolls on unscathed. This sidesteps the paradox entirely, turning time loops into portals to alternate worlds. Imagine a cosmic kaleidoscope, where every twist of a time traveler's hand fractures reality into infinite reflections, each with its own version of events. Could such loops exist naturally? Some physicists speculate that rotating black holes or cosmic strings might twist space-time into these knotty configurations. Intriguingly, certain anomalous cosmic signals like gamma-ray bursts with inexplicable repeating patterns have sparked debate over whether they're echoes of time-looped events. Even the eerie sensation of déjà vu might hint at fleeting brushes with these curves, as if our brains momentarily sync with a version of reality where we've already lived this moment. The implications ripple beyond paradoxes. If closed time-like curves exist, they'd blur the line between past and future, making history as malleable as wet clay. A civilization advanced enough to harness them could send messages to its own past, creating a feedback loop of self-reinforcing knowledge. Imagine a future humanity firing blueprints for warp drives into antiquity, seeding its own rise, a bootstrap paradox where the origin of technology isn't a genius inventor, but time itself. Yet the universe seems suspiciously devoid of time tourists. This absence, known as Hawking's chronology protection conjecture, suggests nature might actively prevent such loops through quantum effects, like a cosmic immune system rejecting temporal contradictions. Or perhaps we're simply too early in cosmic history, and the loops lie dormant in the far future, waiting for conditions to ripen. Whether cosmic censor or quantum fluke, closed time-like curves force us to confront time's deepest enigma. Is it a stage where events play out, or a participant that adapts to the drama? The answer might lie in the quiet hum of a neutron star's spin, or the ghostly flicker of a gamma-ray burst hints that time's fabric is far more intricate and more mysterious than we ever imagined. What if time isn't a dimension at all, but a side effect of the universe's relentless slide into chaos? The thermal time hypothesis flips our understanding on its head, proposing that the arrow of time isn't stitched into spacetime's fabric. It's an illusion conjured by thermodynamics, rising from the uneven distribution of heat and energy like steam off a cup of coffee. Imagine a universe where clocks don't measure some fundamental flow, but simply track the local march of entropy, the gradual unraveling of order into disorder. In places where entropy runs backward, time itself might reverse, turning cause and effect upside down. This idea isn't as far-fetched as it sounds. We already know entropy gives time its direction. Eggs scramble but never unscramble, ice melts but never spontaneously refreezes. The thermal time hypothesis takes this further, suggesting that without entropy's gradient, time would lose all meaning. Picture a perfectly mixed gas where every particle is evenly dispersed. In this state of maximum entropy, no further change is possible, and the concept of before and after dissolves. Now zoom out. Our universe began in a low entropy state after the Big Bang, a cosmic wound slowly healing as energy spreads outward. Time's flow might just be the universe sighing toward equilibrium, but here's where it gets wild. If time emerges from thermodynamics, then regions with reversed entropy, where order increases, could experience time flowing backward. Think of a rewinding film. Shattered glass leaps back into a window, smoke funnels into a cigarette. In theory, quantum fluctuations or exotic matter could create these pockets, though none have been observed. Yet the math allows it, painting a cosmos where time's arrow isn't universal but local, pointing forward here and backward there, like weather vanes spinning in opposite winds. Critics argue this reduces time to a statistical illusion, ignoring relativity's spacetime geometry. But proponents counter that the two might coexist, like seeing a river both as water molecules and a continuous flow. Entropy could be the engine driving time's apparent continuity, while relativity describes its flexible container. After all, even Einstein acknowledged that time loses meaning without change, and what is change but entropy's fingerprint? The most haunting implication: if the universe ever reaches heat-death maximum entropy, time might simply stop. No change, no sequence, just an endless, featureless now. But until then, every ticking clock, every aging star, every memory you form could be nothing more than the universe sighing toward silence, one irreversible moment at a time. Imagine time not as a smooth river, but as a cosmic abacus, each moment a discrete bead strung along an invisible thread, linked to the next by unbreakable bonds of cause and effect. This is the spine of causal set theory, a radical framework where spacetime isn't a continuous fabric, but a sprawling network of events, each one whispering to the next in a chain of before and after. No infinities, no singularities, just a vast, ordered tapestry where every interaction, from a star's birth to your next heartbeat, clicks into place like a gear in an unimaginably complex machine. At its core, this theory sidesteps the mathematical nightmares that plague traditional physics, black hole singularities where equations spit out infinities. Gone, the Big Bang's mysterious 0 point, replaced by a finite, quantized beginning, a first bead on the cosmic string. Think of it like pixels on a screen. Zoom in too far and you hit the smallest unit. Causal sets propose spacetime has a similar resolution, with events as the pixels and causality as the wiring that connects them. It's a universe built not from stuff, but from relationships, a cosmic, this led to that, etched into reality's foundation. But here's the twist: if time is a causal network, who or what does the arranging? Some theorists flirt with the idea of a cosmic processor, not conscious but algorithmic, enforcing the rules that order events. Picture a game of dominoes where each tile must fall in a sequence predetermined by the tiles before it, yet the entire cascade emerges from simple, local interactions. No conductor, just physics' quiet choreography. Others push further, suggesting the network might self-organize, with causality bubbling up from quantum randomness like frost crystals forming on a window, a pattern emerging from chaos without a planner. The implications ripple into metaphysics. If time is just a causal chain, free will might exist in the gaps between events, tiny quantum branches where choices nudge the next bead into place. And what about relativity's flexible spacetime? Causal sets reconcile this by treating order as invariant, While observers might disagree on distances or durations, they'd always concur on which events caused others. It's as if the universe has an absolute script but infinite ways to stage the play. Could we ever test such an abstract idea? Surprisingly, yes. If space-time is granular, high-energy cosmic rays might stumble over its pixels, leaving subtle fingerprints in their path. Others hunt for anomalies in the cosmic microwave background, hunting for hints of the universe's underlying code. And if causal sets are real, they'd redefine not just time but existence itself, a universe where being is doing, and every moment is a handshake between what was and what will be. So next time you glance at a clock, consider this. Those ticking seconds might not mark the flow of time, but the turning of a cosmic page, one crisp causal event at a time. Dark matter isn't just the universe's silent scaffolding. It might be quietly sculpting time itself. We know this mysterious substance outweighs visible matter 5 to 1, its gravity bending light and holding galaxies together. But what if its influence runs deeper? Some physicists propose that dark matter's uneven distribution could warp space-time so profoundly that it creates localized pockets where time flows slower or faster, like invisible eddies in a cosmic river. Picture two clocks placed in different parts of a galaxy, one nestled in a dense dark matter halo, the other drifting in the sparse outskirts. Over eons, they drift out of sync, not because of relativity's usual suspects, speed or gravity, but because dark matter's hidden hand is tugging at time's fabric. These hypothetical time wells wouldn't behave like black holes where gravity's crush slows clocks predictably. Dark matter's effects would be subtler, woven into the background of space-time like faint wrinkles in silk. A region rich in dark matter might stretch time by a fraction of a second per century, imperceptible to humans but detectable by precise enough instruments. Atomic clocks on Earth already account for minuscule time shifts caused by altitude and motion. Future models might need to correct for dark matter's ghostly topography. The wildest implication: if dark matter clumps differently across the cosmos, the universe could be a patchwork of temporal zones, each ticking to its own beat. How could we map these hidden landscapes? Gravitational lensing offers clues. When dark matter bends light around galaxies, it leaves distortions in the light's path, a sort of cosmic fingerprint. By studying these warps in extreme detail, astronomers might reconstruct the underlying mass distribution and predict where time wells form. Some researchers are even designing experiments to measure time dilation between satellites at varying distances from Earth's dark matter halo. Imagine a future where spacecraft navigate not just by stars, but by temporal gradients, avoiding regions where onboard computers might lag relative to mission control. The stakes go beyond practical applications. If dark matter bends time, it could explain why some galactic structures evolve faster than simulations predict. Supernova in dark matter-rich zones might appear to burn slower when viewed from afar, their light stretched not just by cosmic expansion but by unseen temporal tides. Even the universe's expansion rate, a current flashpoint in cosmology, might need re-evaluating if dark matter's time warps have skewed our measurements. But the most tantalizing idea: dark matter might not just influence time, it could be entangled with time's origin. Certain theories suggest dark matter particles are relics from the early universe, frozen in a state that preserves primordial spacetime fluctuations. If true, studying dark matter wouldn't just map time's present contours. It could let us peer back to moments after the Big Bang, when time's arrow first locked into place. So the next time you hear about dark matter's gravitational pull, remember, its grip might not just shape space, but the very rhythm of reality. Invisible, pervasive, and enigmatic, it could be the universe's silent timekeeper, hiding its secrets in the spaces between ticks of the cosmic clock. Watching a pot may make it feel like it never boils, but in the quantum realm, observation can literally freeze reality in its tracks. The quantum Zeno effect reveals this eerie truth. The act of measuring a particle doesn't just reveal its state, it can lock that particle in place, suspending its natural evolution like a bug trapped in amber. Named after the ancient Greek philosopher who argued motion was an illusion, this effect shows how relentless observation can halt time for a quantum system, at least temporarily. Imagine a radioactive atom on the brink of decay. Left alone, it will eventually spit out a particle, but bombard it with constant measurements, and something astonishing happens. The atom hesitates as if aware it's being watched, its decay postponed indefinitely. Time for that particle grinds to a standstill. This isn't just laboratory sleight of hand. The quantum Zeno effect has been demonstrated with atoms, photons, even entire molecules. In one experiment, researchers used rapid laser pulses to peek at beryllium ions thousands of times per second. The result: the ions' quantum states froze mid-transition, their natural oscillations overridden by the sheer frequency of observation. It's as if reality has a refresh rate, and by probing it fast enough, you can pause the screen. The implications are staggering. If observation shapes time's flow at the quantum level, could advanced civilizations harness this effect to manipulate time itself? Some theorists speculate yes. A society mastering quantum control might engineer temporal traps, regions where particles, or even macroscopic objects, are suspended in perpetual observation, their clock stopped while the universe marches on. Picture a vault where light pulses bounce between mirrors billions of times per second, creating a zone of frozen time where relics or information could be preserved indefinitely. Or consider a spacecraft shielded by quantum sensors, its hull constantly measured to delay entropies where, effectively extending its operational lifespan far beyond natural limits. But scaling this effect beyond tiny particles poses colossal challenges. Maintaining coherent observation of complex systems requires staggering precision. Any missed measurement could collapse the delicate quantum freeze. Worse, the energy demands might be astronomical, like trying to illuminate every corner of a pitch-black warehouse with strobe lights fast enough to simulate daylight. Yet the universe offers potential workarounds. Black holes, with their immense gravitational fields, naturally slow time near their event horizons. Could their extreme physics amplify the Zeno effect, creating pockets where time crawls or even stops? Some models suggest that under the right conditions, quantum observation and gravity might intertwine, turning entire regions into temporal stasis fields. The most mind-bending possibility, if consciousness plays a role in quantum collapse, as some interpretations suggest, then focused observation might not just freeze time locally, but sculpt it. Ancient meditation practices claiming to alter time perception could be crude echoes of this principle, where heightened awareness subtly bends the quantum fabric. Future technologies might refine this into a science, using directed attention or AI-driven measurement to tweak time's flow like a dial. For now, the quantum Zeno effect remains a tantalizing hint, a whisper that time's rigidity might be an illusion, and that with the right tools, its gears could be jammed, slowed, or even reversed. Whether humanity ever unlocks such power is unknown, but the mere possibility reshapes our cosmic perspective. Time may not be the universal constant we thought, but a mutable construct waiting for the right observer to press pause. What if our universe isn't flying solo through the cosmos, but paired with a silent twin, a mirror reality where time runs backward, stars burn with antimatter, and every event we remember as history unfolds in reverse? This is the Biverse Hypothesis, a radical reimagining of existence that turns time's arrow into a cosmic optical illusion. Picture two films projected back to back on the same screen, one showing a cup shattering, the other showing the shards leaping back into place. From our perspective, entropy increases and cause precedes effect. But from the twin universe's viewpoint, we're the ones living in reverse, with smoke funneling into cigarettes and sunlight retreating into the sun. The math behind this idea isn't science fiction. Particle physics already reveals eerie symmetries between matter and antimatter, like electron and positron pairs, identical in mass but opposite in charge. The Biverse hypothesis takes this further, proposing that antimatter isn't just a rare byproduct of particle collisions, but the ordinary matter of a parallel cosmos where time flows the other way. This could solve one of cosmology's biggest mysteries: why our universe contains so little antimatter despite the Big Bang presumably creating equal amounts. The answer: it's all out there, just locked in a mirror universe, forever separated from us by the one-way glass of time's arrow. Imagine sending a clock into the boundary between these twin realities. From our side, it ticks forward, from theirs, it ticks backward. But here's the twist: observers in each universe would perceive themselves as moving normally, while the other's time runs in reverse. It's like two people standing on opposite sides of a mirror, each convinced they're raising their right hand while the other lifts their left. This symmetry isn't just poetic, it's mathematically elegant, resolving quantum inconsistencies by treating time's direction as a relative property, not an absolute rule. Critics argue that such a universe would leave detectable echoes, perhaps faint particle interactions at the edges of our cosmos where the two realities brush against each other. Some researchers even speculate that certain high-energy cosmic rays, which arrive with unexpected properties, might be refugees from this inverted realm, leaking through microscopic cracks in spacetime. Others hunt for anomalies in the cosmic microwave background, the afterglow of the Big Bang, which could bear scars from an early entanglement with our twin. The most profound implication: time's arrow might not be written into the universe's laws, but an accident of perspective. If the Biverse is real, then free will and determinism could flip depending on which side you're viewing from. Your choices feel open to you, but predetermined to your mirror counterpart. Even the Big Bang transforms from a beginning to a turning point, a cosmic pivot where two timelines unfolded in opposite directions like wings from a shared spine. So the next time you watch steam rise from your coffee, consider this: somewhere beyond the veil of space-time, a twin universe might be watching that steam sink back in, both of you equally convinced you're the one moving forward through time. The Biverse hypothesis doesn't just challenge our place in the cosmos, it redefines what it means to move through time at all. Picture the universe not with a bang, but a whisper, a cold, silent fade into endless night. This is heat death, the fate awaiting our cosmos if dark energy keeps accelerating expansion. Stars will exhaust their fuel, galaxies will drift apart like embers from a dying fire, and black holes will evaporate into faint Hawking radiation. Eventually, every particle will be so isolated that no interactions remain: no light, no heat, no change. Time, stripped of events to mark its passage, would become meaningless. No ticking clocks, no orbiting planets, just an infinite void where before and after lose all distinction. Yet this bleak scenario hinges on our current understanding of thermodynamics. What if unknown forces lurk in the vacuum? Quantum fluctuations, tiny bursts of energy from empty space, could theoretically birth new particles even in a lifeless universe. Given enough time, and enough here means numbers so vast they dwarf the current age of the cosmos, these fluctuations might spontaneously assemble a new Big Bang from the void. Think of it like a frozen lake cracking under its own weight. The sheer scale of eternity could fracture equilibrium, restarting time's clock. some theories propose even wilder resurrections. In a hypothetical cosmic bounce, the universe's expansion could reverse not through gravity's pull, but via a phase transition in dark energy like water freezing into ice, flipping repulsion into attraction. Alternatively, higher dimensional physics might allow our universe to tunnel into a fresh space-time bubble, leaving heat death behind like a snake shedding its skin. These ideas stretch credibility, but they reveal a tantalizing truth. The end of time might not be absolute, just the limit of our current models. The most haunting question isn't whether time can restart, it's whether time as we know it would even apply. A reborn universe might operate under alien physics with no memory of its predecessor. Our laws of causality, entropy, even the arrow of time could be local quirks irrelevant in the next cosmic cycle. Like an actor unaware the play has ended and a new one begun, we might be mistaking a single act for the entire performance. So while heat death looms as time's graveyard, the universe has surprised us before. From quantum foam to hidden dimensions, nature's playbook is far from exhausted. Whether time ends forever or merely transforms, one thing's certain: the final chapter hasn't been written. It might not even be in the same book. From the fiery birth of the cosmos to its icy twilight, these 28 revolutionary theories have stretched our understanding of time to the breaking point and beyond. We've ventured through holographic universes where time is a shadow, danced with particles that erase the line between cause and effect, and glimpsed realities where clocks tick backward in mirror dimensions. Yet for every answer, new questions emerge like ripples in space-time. Is time real or just the universe's most convincing illusion, a fundamental force or a side effect of quantum whispers? The beauty of this mystery lies in its defiance of simple solutions. Each theory is a flashlight in a vast cave, illuminating one facet of the enigma while leaving the rest in tantalizing shadow. What's astonishing isn't just the diversity of ideas, but how they intertwine. The same quantum entanglement that could explain time's arrow also hints at a universe woven from information. Black holes, those cosmic paradox machines, might hold keys to both time's origin and its ultimate fate. Even the eeriness of déjà vu finds echoes in theories of branching timelines and folded chronologies. It's as if the universe is whispering clues in a language we're only beginning to decipher, a puzzle where physics, philosophy, and perception collide. This isn't just academic curiosity. Unraveling time's secrets could rewrite everything from quantum computing to interstellar travel. Imagine engines that manipulate space-time like origami, or clocks that tick differently for each observer based on their quantum state. The practical applications are as boundless as the theories themselves, if we dare to think beyond the ticking of ordinary clocks. So where does this leave us? Standing at the edge of discovery, armed with equations and questions, maybe time is all these things at once: a dimension, an emergent rhythm, a cosmic mirage, or something stranger still, waiting for the next Einstein or Hawking to give it a name. The conversation doesn't end here. It evolves with every experiment, every observation, every bold idea tossed into the ring. Which of these theories speaks to you? Do you see time as a river, a tapestry, or a code? Drop your thoughts below. We're all detectives in this grand cosmic mystery. And if your curiosity is as boundless as the theories we've explored, hit subscribe and join us for the next adventure at the frontiers of science. The clock is ticking, but the exploration, that's timeless.